Hello everyone, my name is Anthony Shivkumar, and in today's video I want to do something slightly different. I want to talk about the lessons learned in this full CPU LLM series in terms of what did I do in 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 working with the GPT-2 C project, and kind of like the mistakes that I learned on the way, and what I would do in order for me to kind of like get this working in a much more dynamic way. Because what's happening is that my inference is working perfectly, it's in full compatibility with PyTorch, but when it comes to back propagation, the way I've coded is a little too long a file, and then debugging every single numerical precision is now causing I'm wasting too much time in debugging to a point where I'm finding this not worth the efforts. So let's go through the whole process of the kind of like things that I've been doing in terms of cleaning up all the numerical instability, like comparing every single layer in terms of inference and backprop, checking whether the KV of every single part of the whole neural networks, the algorithms and the computation match that of PyTorch, whether it's KV, whether it's the MLP, whether it's the layer norm, and kind of like doing all the test cases and giving me kind of like the idea that when I do work on my next project, I will be able to take all of this ideas so that I don't repeat the same mistakes again. So let's get started. I will show you a demo of all the test cases that I built around this particular application. And then I will most likely archive this particular project and then work on the next kernel engine that I will be talking about as well in the later part of this video. So let's get started. So what I have over here is my original, GPT-2 in C code. And what I've done is, because there was a lot of numerical instabilities, my goal was to kind of like do a very thorough check of where am I going wrong. So one of the things is, if you download and clone the repository, the C transformer repository, you will see something such as you can do a make help, and then you'll get a list of all the kind of commands you can test on this particular repository. And one of the things that you could see is that I've written a lot of validation for the forward pass, just to make sure that everything is kind of like numerically aligned with PyTorch. And I've done the same thing for the backward pass and training, and kind of like getting a sense of if there is a bug in my code, which part of the computation is having that bug. Because once you solve that particular computational bug, say for example if it's QKV, then that's fixed for all the layers, right? So there's just few computations that you need to make sure that it's in sync with is in full parity with PyTorch. And that's the kind of testing that you're doing, is like checking whether the weights are loaded properly, whether the embeddings are loaded properly, which is the the weight tying and the dense embeddings. Then whether the layers, in terms of are they performing, if you have 12 layers, are they doing 12 layers of computation? Is your QKV working? Now we go right into the layers and see if the QKV is working. Then if you see whether the attention is working, and then you can validate whether the logits, the end of the whole pipeline, whether the tokens that are generated are accurate. So that's the kind of like methodical testing that I did for the forward. Similarly for the backward, but the backward started to get a little bit too complicated, because you have to do the forward and then get all those weights and then compute the backward. But the backward also has another issue, is because we are doing gradient accumulation. The error could be in part of like the accumulation. The error could be in part of the strides. It was just too much things to kind of like boil down in the way I had done this particular project, to a point where I felt like I need a better way to test this, because this was done towards the later half of my of almost completing the whole project. And in reality, I think testing should be partly baked into the whole process of designing your own, kind of like mini nano PyTorch, if you want to so call it. So let me do a test and show you what that might look like. So I'm just going to do a make a validate all to get a sense, like how does the inference engine is validated in terms of in parity with PyTorch. So yeah, it's compiling with the AVX512 flag, and then we kind of like give it an hello world, which is kind of like 2 tokens, and from there we're loading PyTorch, and it's giving us some warnings. And here we're saying, okay, are the the tokens that is kind of like we're basically taking the tokens and put them into the format that, you know, our C transformer works. And we're kind of like doing a basic kind of like, is it loaded properly? So we're reading, you know, things like reading the token embeddings. Is the first 10 values looking the same? Is the dimension looking the same? Then we go and you're seeing the positional embeddings. Is the positional embeddings looking the correct? And then we're just doing a comparison. Is there any errors? The total difference is 0. Total difference is 0. So that means we've loaded the weights into our C inference engine accurately. So now we can say, okay, now where else would be the error if there is an error, right? So then we go and do another validation on the embeddings. We're looking at the Hugging Face PY-torch values, and we're looking at my C transformer values. And we're saying, oh, the difference is 0. That means there's no errors. So I just do this, you know, methodically for every single part of that computation. I do the same thing for this area, which is the output comparison, which is on the tokens. What's the error? Some of the errors is almost 0. Some of the errors is, you know, 2 raised to 10 raised to minus 7. So 0.00001 point something, right? So we're looking at pretty accurate, what do you say, even at the end of the logics, once it goes through all the computation and all the layers. And all these errors can come from the way things are kind of like, you know, done on the hardware level. Like if you're using the AVX512, the numerical precision will be slightly different from, say, if you use scalar or you just use the floating point 32 execution unit. Each one of those execution units at the hardware level might produce, you know, a little bit of numerical inconsistency at the 10 raised to minus 7 error, you know. So those are the kind of things that we want to make sure that if there is an error, or if there's any difference, I won't say error, that difference is so small. 10 raised to minus 7 is you know, is acceptable for you to get the right logics. And then we put that hello world, and then the GPT-2 kind of like gives us the Hugging Face logics and my logics, and it's more or less, you know, exactly the same. So that's a good validation of now everything is in parity of PY-torch for inference, and we're kind of like checking, you know, what the overall differences of the top 10 is 0.0013, which is, you know, all pretty much the same as Hugging Face, and here we go, right? So this gives us the full inference pipeline and saying that now the C code is in full parity with the Hugging Face. Now let's go and try to do the same for the backprop, and this is where the backprop was starting to, you know, get a little bit, I would say, wasn't performing as well as I would like. So here when I do the make compare training, or maybe we could do a make validate backward, we will see that even in make validate backward, let's go through this. So it compiles, it loads the thing, it'll go through the full inference, and it'll go through the backprop. And even in the backprop, the errors are kind of small, but it's still not performing. It's not training properly. There's some bug somewhere. And that's where it's kind of a little perplexing as to where that bug is. You know, is it at the computational level? Is it at the aggregation level? Is it at the atom optimizer level? Is it by, you know, loading the weights and updating the weights at the, you know, after the backward pass, the first epoch is kind of done? Is the weights kind of like updated accurately? So there's too many places where there could be a bug that it's hard to pinpoint. And at the same time, I also realized that so yeah, let's go through this process now. So once we do the backward error, what we've done over here is, yeah, so the loss is perfect because, as I mentioned, the inference is correct. So once you go to the full inference, then you take the error of your logics of what you're trying to predict and see whether they, and you basically kind of minimize this error, right? This is the Hugging Face loss, and this is my C loss. That means the inference engine is almost as accurate as a Hugging Face. But then it gets a little bit, you know, the differences start to like kind of show up, which is the layer norm gamma versus the final layer norm gamma. Almost the same, but there's an error. You know, these errors are starting to, they're pretty small, but they're still starting to be noticeable once you start to do the gradients, and the gradient starts to flow through the whole backprop. So even now we are 0.175, 0.083, and now we're starting to see little errors here and there, and the errors keep accumulating. And every part of this, there will be some bug, and I'm trying to like figure out, it might be a stride issue, it might be a memory issue. And in some cases, the error is very small. It's 10 raised to minus 6, right? And in some cases, the error is a little bigger. In some cases, the error is, so it's kind of like a little inconsistent out here to a point where I've been doing tremendous testing with comparison with Hugging Face, and in many cases it's not really I'm not really progressing. And like look at the embedding weights, which is a tying thing. The error is almost zero, right? Like we're looking at 10 raised to minus 9 at this point in time. So having said that, that's kind of like what I've done over years, doing a lot of thorough testing, and found out that this is not the most efficient method, because one of the things that I did with this particular project was that I did the full inference, then I did the full, then I tested it out, it was working, then I did the backward inference, and actually there was a bug even when I did that, but it was looking like GPT-2, so I didn't really look into it too much, and then I did the backward, and then things started to look like they were working. But then after some time I was noticing that something is not looking right, and then I had to do the full inference testing and found that there was a small bug in my inference to fix it to be full parity with PyTorch, because both are kind of like, the GPT-2 original model is also not, it's not coherent in many ways. So when you just see English coming out of the GPT-2 model, you kind of like get a sense of, okay, it's performing as well as GPT-2 can, right? So, but there was a bug in there. So I'd had to do the full testing of, finding out where the errors are on that forward inference, and then do the same thing for the backward inference. And then I realized, like, forward of one computation, backward of one computation started to get a little bit, I don't think that's what I would do in my next project as such. So I've learned a lot of this. So I'm just going to go to a presentation that I made for myself, and happy to share that, to kind of like, digest all that information, capture all the learnings that I've done. I'll be archiving this project, so that, I can share a little bit about that lessons learned, so that when I perform the next, my next project, I'm going to take those lessons and kind of like improve on it. So yeah, this is like what went wrong with my GPT-2. First and foremost, it's a lot of lines of code. I wanted to make this as kind of, I was inspired by Karapathi's video, I'll be honest, and he had everything in one line of code, but it didn't have HPC, so it was kind of like not the best way to kind of like, it was lots to learn from, but it wasn't the thing that it was resonating with me in the way I would want to solve the video. So in that sense, it kind of like gave me the ability to kind of like think through this a little differently, but still have that one line of code, if you so want to call it that way. So the original goal was to build a full transformer architecture, the both full forward pass, the backward pass, use as much vectorization as possible. In this case, AVX512. I don't have access to AMX and all the other cool vectorization, but at least at the compute that I had, it had AVX512, and validate against PyTorch to see if, it worked. Why C? Generally, it is one of the languages that has the lowest amount of abstractions. It's optimized for embedded systems. If you want to take this code and train this and run this on an embedded system, you're very much likely to have C work and be compatible when it generates the instruction set for that embedded system. It's ubiquitous in the embedded world. It's ubiquitous in the HPC world. Operating systems, you want speed, you want performance, you don't want abstractions, you want to be as close to compute. C is generally the choice. And if you're coming to my channel, I don't need to explain why we need C. Everything about what I do is C, because of any embedded systems you take is going to be in C, right? So this took me around 10 weeks of development, around 2 months, 2.5 months. And kind of like broke this apart into, what the tokens were doing, loading the tokens, doing the positional embedding, doing the matrix multiplication, then layer norm, multi-head attention, then the multi-layer perceptron, then the GELU activation, doing the residual connection. Then you start to implement the derivatives of all of these, in the backward pass, and then you kind of like, create that training loop. You do it once, it seems a little bit too much. You do it twice, it becomes easy. It's as much as AI is, all about artificial intelligence and general intelligence. I think the way I perceive it is that it's a great augmenter, and more importantly, it's able to speed up this learning. Something like this, if I had to go out that, go to a top university, get the top professors to do this, I think AI can augment a lot of that for me in terms of like, I need to know the derivative of layer norm. Sure, I can derive it, right? But I'd rather have someone just give me the layer norm derivative, right? So things like that. If I could derive it, yes, absolutely. Get the applying the chain rule and applying the full, the full process. you can still do it. It's not, 12 standard math is basically all you need for all of this. But then there's that little bit of speed in terms of precision, and when you're writing in C, every addition, subtraction, multiplication, addition, a symbol here, a sign here that changes the whole formula. It doesn't work, and that's where kind of like the AI boosts your speed. So there's a lot of AI help with me to augment my speed. Not much vibe coding. I would say a lot more. I want to do this positional encoding, and I'll write my 3-4 lines of code, and then the AI will kind of like complete it. It'll have bugs, and I'll be like, you didn't apply SIMD, single instruction multiple data. Can you load this into a process, into the registers? Then it will be like, it'll do something, and I'm like, okay, this is not aligned. Can we use the proper bump allocator? But it still was much faster than I would have done in many cases, right? And what worked? The perfect forward pass, as I mentioned, the difference was almost negligible. The loss function was perfect. Fast inference using the vectorization, and we're using OpenMP parallelization. And the validation started to have a little bit of, we had a lot of validation, component by component, numeral diffing, the comprehensive test suite, and kind of like, having this kind of like method of testing, especially at the lowest level. And of course, AI can help you speed that up. So it's not adding too much to the whole process, is what really worked very, very well. And it's what I'm really learning from this whole process. What has issues is the kind of like the training loop. What happens is that after the second iteration, we can go there quickly. So for example, let me see if I can still load this. Let's do a training loop as we speak, and then we can come back to the slide later on. Let's do a proper training loop. Let's do okay, let's try make train PyTorch. Actually no, make validate backward. Let me do a make backward. Yeah, let's try this one. Let me see if this even works. And then what I've realized, there was a loss function, and that loss function in the second epoch just went to like just exclamation mark, and at that point I kind of like, yeah, it was starting to get a little too tedious, as I mentioned. So let this run. I'm hoping this does the proper forward and backward pass. Yeah, and then again, it was hidden somewhere in these 15 lines of 15,000 lines of code, and it's most likely either a gradient accumulation or I don't know. I wouldn't say lost computation, but somewhere in there was an error. There were certain differences, but some of them were acceptable. Some was high but tolerable. But overall, as these things, keep accumulating, the numerical precision started to get, a little bit, yeah, it wouldn't work. So then what I came up to know was that validation is really everything, right? Because this itself caught a lot of bugs. As I started to do this training and validation of checking every part of that, the query key values, the multi-layer perceptron, the positional embeddings, the wait time, and checking out, what's the error, what's the mean, what's the differences, where did it fail, started to become the most important toolkit when you're designing your own kind of like PyTorch engine. And the problem was, one could say code complexity, but the more important thing is that I didn't really realize that once you do this, it's just an accumulation of computation. So in the beginning, I just thought of it as like, oh, this is GPT-2, or this is Llama 3, or this is XYZ. But I think the more you do it, you realize it's just building blocks of computation, which now that I know about it, makes it easier. So it's kind of like, forward pass had a lot of lines, backward pass a lot of lines, the optimizer had its own lines. And once you start to like, put in a lot of these codes, and I put a lot of debug, where's the bug? Is it in the optimizer, the back prop, is it a training loop, is it a forward pass, memory management, threading, who knows? So one of the things that I'm learning towards now is what I did wrong was I did all the forward pass, then tested the forward pass, then all the backward pass, and tested the backward pass, and then debug everything at once. What I would be doing right now is write the RMS norm forward, I write the RMS norm backward, then validate it. So I can go computationally and do the forward and the backward. I could do GELU forward and backward. I can do MELU, multi-layer perceptron forward and backward. And I can do this with dummy data because I'm checking for numerical precision. It doesn't matter whether my array has got, random numbers, but I need to make sure the mathematical precision is accurate. And I can do that very quickly with PyTorch for every single computation. And I can then add in vectorization and high performance compute at this level itself. Because if you can isolate computation is not the problem, then it's all about connecting those computations. That might be a slightly easier way to debug because now at least you've eliminated the possible computational problem. And then you can move to the next component and then never have more than one unknowns, right? Like there you go. So when a bug appears, you know exactly where it is, the current component. You never debug 15,000 lines of code. And validation is an investment. Yes, it is, it can be faster to kind of like, it does take time to spend on the validation, but then once you start to like debug, you save a lot of time, right? So when you are writing, yes, it's fast, but then by the time you test, it'll take so much more time because you don't know where the bug is. I'd rather just write the test case in the beginning, and then kind of like the next benefit, would be a little, hopefully better. And I don't think the testing was enough, though I had, testing for embeddings, for QKV, attention, layers, backward, PyTorch, and all that cool stuff. There's still a bug, right? So we validate components in isolation, but never validate the complete training loop end to end. The bug was in the integration, not the components. I mean, hard to say at this point in time where the bug is, but overall the testing was not enough, even though it seems comprehensive in hindsight. And what was inefficient is that, notice if the loss is 0. Add printfs. Notice the loss, when I say loss is 0, as in the loss difference between PyTorch and my C code. Adding a lot of printf statements, rebuilding every time, run analyze and find a suspicious value, then add more printfs. And sure, this is easy, but it's still not the most efficient way. I do believe the better debugging method is to kind of like, as I mentioned, you can do the automated gradient checking, and then you kind of like, and then find the differential testing. There are like these methods of which you can kind of like validate every numerical precision from a whole end-to-end process. So you can validate at every step. I don't have to wait for the full training loop to fail and then catch the divergence immediately. So these are the kind of like ideas that I'm kind of, going to be implementing in my C kernel engine. The memory layout does matter. 64 bytes aligned, significant performance boost for the AVX512. Of course, if you do proper tiling and then you get the right layouts, so that you're constantly having things that are constantly being computed in hot cache. There's lots to it. You can't just say 64 alignment and put vectorization. It's going to suddenly magically speed up. There's also how do you like lay out this whole thing by blocking and all that cool stuff. It gets into the real computation of how GEMM kernels work, the general matrix multiplication. I've done a whole video on it, and that's just touching the surface. Continuous memory block, head major layout attention, better cache locality. Then you want to use pages, and then you're trying to like get the speed up of using OpenMP, speed up from memory alignment, cache hit rates, and all that cool stuff, right? So all of those things still matter. Nothing wrong with all the stuff that's been done. What we have is a bug in the computation. So here, the PyTorch for training is also pragmatic. I don't mind using PyTorch for training. Though once I do my whole engine, I would start to like focus on how my C engine for CPUs can probably, offset some of the bloat of PyTorch. But the whole idea is you get a training data, you can use PyTorch for training, get the checkpoint in, export that checkpoint to C. Let's test that weights on the C inference engine, and then you can have that fast inference. So PyTorch can handle the backprop. It's more mature, it's more optimized. This definitely does not have bugs, and the C handle can do the inference perfectly. That could be one way of what this GPT-2 project can be at this point in time. It could be just an inference engine, though it needs a little bit of more optimization, but it's archived, so I wouldn't recommend you using it for inference. It's not going to be beating Llama CPP anytime soon. There's a lot of optimization that's on the table that's not been tested, but this is one process that I could do. And then the most important thing I think is seeing patterns. This is one thing that I'm really, I generally feel that I'm really good at, and it comes from, I think, when you start to like solve massive, diverse problems, like whether it's doing embedded systems or web development, and even doing GPT-2 and C, the patterns come, and it's very different from someone telling you the pattern versus you figuring out the pattern. I think it just hits you very differently, and this is where you start to see how all of these models work, whether it's the GPT-5 versus GPT-2. These models are just a bunch of computational graphs in some shape or form, and that's what PyTorch is. But as I said, it's very different from someone telling you it versus you kind of like revealing and feeling that. That's kind of like what this has taught me. So every layer had a forward function, it had a backward function, memory allocation, validation script, unit test, numerical precision handling. Every model needs a graph structure directed at acyclic graphs, memory planning, kernel fusion, debugging tools, performance, multi-architecture support. So these patterns suggest a kernel-based domain-specific language architecture. So I don't have to write the same boilerplate for every component, build one's composed model from kernels. So this is where I'm starting to lean towards, and I'll talk about kernels shortly. So by these numbers, there's, as I mentioned, because I had to do all of this in one whole go as one component, the C code is mammoth. Then we have Python, and then we have the documentation, and we have the test cases. The number of and you still have a bug, right? So when you look at this, the amount of effort going into doing this as one component, this like GPT-2, is not as practical as doing it as a kernel method. And the distinction archive is, I'm not going to fix this bug. The bug could be anywhere. Putting printf statements is not going to really help me now. The debug path is diverging from production. Would take weeks to isolate. And I'm going to start fresh, but I'm going to do this a little differently. And the best code is basically the code you delete. It's not necessarily a failure. It's kind of like learning. The next iteration is going to be hopefully better because of the experience that I've learned from doing this, right? So what's next? In here, I'm going to do things like a kernel. The kernel is a set of libraries where you'll have things like RMS norm. You'll have, the rotatory positional encoding, matrix multiplication, softmax, group query attention, the Swiglu activation. And then you build a graph and you say, okay, this particular, say this is GPT-2 or the Quen model, it requires RMS norm, it requires, rope, it requires softmax, it requires a group query attention, it requires, Swiglu. And then you basically do a graph builder, graph execute, graph optimize, and then you'll get Quen.c, llama.c, GPT-2.c. Very similar to how PyTorch works. So I'm building kind of like a nano PyTorch, and I think this makes a lot more sense to me. So the new architecture for my kernel first design is going to be, each kernel is going to be a single file, which is going to be 200, 500 lines. It's going to have forward, backward. It's going to have the validation. It's also going to have vectorization. All the high performance compute parts of it is going to be in there. Of course, chaining all them together and having the fused multiplication and add is also a huge part of this whole process. So to get that performance, we'll be talking a lot more about that as the C kernel engine kind of like, evolves. And the immediate validation is, I write the RMS norm, write the backward, test it, see what the difference is. If it's passing, move on. So it kind of has this separation of concern using this graph model. And the old versus new, this was monolithic. This is going to be more modular. This was mostly forward first, then backward later. This is going to be forward, backward together. Memory was more or less manual management. I wrote the whole, bump allocator, but this is going to be done through the domain-specific language with the graph builder, DSL. The model was only for GPT-2. This should be multi-model because now we're just going to add in computation, and but you need to have like a library of your kernels. Debugging was printf. Here the debugging will be part of the per kernel, and then of course we'll be doing other debuggings when we assemble the whole graphs together. And the validation after building was a large section. This is going to be immediately after each kernel. So the components test only, and this is going to be components plus integration plus gradient checks. So the idea is that, say you have layer norm, you have multi-head attention, you have MLP, you got GPT-2. So you take it from the shared kernel. Then if you want RMS norm plus, rotatory positional encoding, plus group, query attention, plus the Swiglu attention, you just group them all together from the kernel library, and you get Llama 3, same thing for Quen 2 and all that cool stuff. So that's the idea. So the built-in debugging tool, I'm hoping I'm going to have a lot of debugging for gradient checking, for graph visualization, per kernel profiling, memory visualization, and all that. So that all the good stuff of what I've done is going to be taken away, and all the inefficient stuff, especially in terms of testing, is going to be adopted to this new version of my C kernel engine. So the development timeline, I'm still working on this. This is just for me to kind of get a sense of the speed at which I want to operate in. And so one of the things, the most important thing is the validation is not optional. Code complexity is generally the enemy. So I want to do this by component by component. Keep the file small. Forward plus backward together. This I think is the most important part. I don't want to just do forward because it's very easy to be lazy about the backward. Oh, there's calculus. How do you do this, right? But I think once you start to get comfortable with the whole backward prop and the loss function and derivative of loss with respect to every component and every variable and every gradient, you do it a couple of times, it becomes a lot more. It becomes less scary. PyTorch for training is smart. Don't reinvent the wheel. This I'm sure, but at the same time, I would say once I get all of these things working together, I could change this. But for now, I'm still going to be relying on PyTorch for training. And the patterns are just better architecture. So after seeing patterns repeat, build abstractions, the kernel-based DSL prevents code duplication. So yeah, what I've accomplished, just to get a sense, I'm putting myself a pat on the back, just at least for my motivation, so that I can go and move on to the next project. Is that this was not particularly a failure because the inference works, so it helps me know that at least what I know about GPT-2 is working with PyTorch, so that I have a very decent understanding of how that works. I'm able to validate every component and see the error, at least for the inference. Optimize using vectorization and hardware vectorization and the open multi-parallel libraries. Learn numerical precision, build comprehensive validation. So there's a lot of things that I've learned that's kind of that I can take away from it. So though I'm starting from scratch from a code standpoint, I still have now there's memory of all the things that I've learned that is going to be part of that experience in building the next version. Yep, and that's pretty much what we want to show you. And let's go and look at the test case over here. So in this particular case, we run this test case. We ran this a little bit earlier. Let me go and check where we were. Okay. Yeah, so we did the make validate backward. We did the hello world. Here we have the errors. Again, we have all the errors. And yeah, here we're doing the layer norm backwards. So we're doing the the backwards of the derivative of layer norm, beta, final layer norm x. See, the errors are slightly very, very small. The derivative of layer norm dy and dy, and then gamma, and then beta. So as I mentioned, there was a lot of testing done, and then eventually it started to, then you do the layer loss, then we do the loss function and all that stuff. But over time, once I did the full forward and backward training, it started to, what do you say? Yeah, once I started to do the full backward, forward and backward, the loss just started to go 0 and it started to give exclamation marks, and I was like, yeah, whatever. So yeah, that's really it. I will show you one more thing, what I'm planning to do right now, just to get a sense of my library. So here, this is the C kernel engine. You can go over here, go to the Ansher repository, and you can search for the repositories and go and check the C kernel engine. I've already started working on this, and I've just basically created a small little image from Gemini using the new banana, whatever you want to call it. And you can go to the source, and then you can see the kernels. And here, I'm starting to write all my kernels. So here you can see the GELU kernel. A lot of it is just copied from my GPT-2C. So because the things that work, I'll take it. Layer norm, multi-layer perceptron, RMS norm, sigmoid, softmax, Wigloo. So you can look at the GELU. I've taken this, from the GELU backward, and then doing the backward, and then doing the forward. So you can kind of seeing that I'm doing both at the same time. Same thing for the GEMM kernel, the native parallel. And there's 4 different types using some form of vectorization. Layer norm, you're doing the layer norm native serial, layer norm forward roll slice, which is kind of like unrolling for the registers, and there's unroll for basically using the 2 FMAs, the 2 fuse multiplication and add. And then we do the match precision, and then we do the layer norm backward, and all that cool stuff. Yeah, so working on the C kernel 2 version 2. Have a look at it, and hopefully you like this video. If you liked it, do subscribe, put your comments on here below. I'll be doing a video on certain aspects also of the transformer, especially if you want to know more about what's the difference between multi-head attention and group query attention, or if you want to know what's the difference between RMS norm and layer norm, or the difference between GELU that they use in GPT-2 to the swiglu activation function. What's that difference? What the derivatives is? So all those details are what's the difference between, say, the prefill stage of an inference and the decode stage of the inference. If all of those details kind of like matter to you, please comment below. I'm more than happy to kind of like dive into one of those narrow niche parts of every part of the transformer to kind of like hone in on that skill, so you become better at understanding these details. And then at the same time, I'll be building up the kernel and kind of testing this out with other models to get a sense of the adaptability of the C kernel engine. So until next time, take care, and hope to see you guys soon.